Hello folks, today we're going to be talking more in depth about three-dimensional rotations. This is also covered in Robotic Systems Chapter 4. So we've talked about how to operate on coordinate transforms, and now we're going to start talking about the issue of interpolation. We're going to be worrying about movement a lot in this course, and so especially when we're talking about three-dimensional rotations and how to represent movement with three-dimensional rotations, we're going to have to think more carefully about how to do things like interpolation as well as differentiation, although we'll cover differentiation in a future course. So we're going to start by looking at the general problem of interpolation. So anytime you want to build a movement, the kind of basic primitive of representing that movement is that of interpolation. So in a Cartesian space, this is relatively straightforward. If we have 2 points A and B, and we want to trace out the straight line segment between those, we can set up an equation such as this one here that takes a parameter u in the range 0 to 1, such that if I were to feed in the u is equal to 0, I would get A, and if I were to feed in u is equal to 1, I would get B, and in between I linearly interpolate. So x of 0 in this case would be A. If I were to then increase u slightly, I'd then march along this line segment. If I were to put in 0.5, I'd be halfway there, and then finally if I set u is equal to 1, I'd be all the way to B. So essentially we want to be able to do this type of thing, but also for rotations. So things become a little bit more complex when we start talking about angular quantities. So even in 2 dimensions, this isn't completely straightforward. So if we wanted to blend smoothly from some angle to another angle, and we have this parameter u, we could just try doing the same formula as before, essentially with basically having a linear interpolation between theta to theta prime. But if we were to do this naively, and we had theta is just a little bit above 0, and theta prime is almost all the way to 2 pi, then the naive linear blend is going to go all the way around this circle, essentially, and so we're not going to take the smarter path, which is to go clockwise around the circle from theta to theta prime. So the key thing is that we want to make sure that we have a geodesic blend between these two. Now, geodesic is something that you may have not heard before. It's a concept dealt with in topology. And the main reason why we have to think about different ways of blending is because the topology of the space of rotations is not the same as Cartesian space. Topology deals with how points are connected to one another. And here you can see that from 0 to 2 pi, those 2 points are connected even though in the straight line segment, from 0 to 2 pi, they're far apart. And so the topology here essentially needs to deal with the wrapping around from 0 to 2 pi. And so in 2 dimensions, this is not too difficult. Essentially, we have 2 different ways of going. We can either go clockwise or counterclockwise, and we just want to pick the route that has the minimum distance. And so we just basically compare which one is shorter and pick that one when we're doing interpolation. Now, things become a bit more complex in other topological spaces. And in robotics, we deal most primarily with 2 unusual topological spaces. The first one is the space of 2D rotations, and the second is the space of 3D rotations. There's a lot of terminology to deal with these different topological spaces. We already know how to work with the real number line as well as Cartesian space. Now, you may also see S1, which is the boundary of a circle in 2D. There's also S2, the boundary of a sphere in 3D. So the most familiar S2 topology is that of moving around on the Earth's surface. And although that is interesting, we're going to be focusing today on looking at SO3. This is called the special orthogonal group in 3 dimensions. So this is the set of 3D orientations. We're also going to eventually look at SE2 and SE3, which are the space of rigid rotations, rigid transformations in 2 and 3 dimensions. Now, SE2 and SE3 we use a lot, but essentially the only complex bit about dealing with SE2 and SE3 is the rotation component. That's because they are essentially a Cartesian product of a rotation space and a Cartesian space. So this Cartesian product means that you pull one element out of one space, pull another element out of the other, and you package them together. And so we can see that SE2 is homeomorphic to SO2 times R2. That means that if we pick an element of SE2 and we pick some element of SO2 and R2, then there's a one-to-one correspondence between those different representations. The same thing goes for SE3 and SO3 cross product with R3. So basically a rigid transformation is just a rotation plus a translation. So the complex bit here is really dealing with that rotation component. So SO3 is rather complex. You can think about them as 3x3 rotation matrices. However, the 9 entries of these matrices need to be constrained. That is, they have to deal with the orthogonality constraint of a rotation matrix, and we also need to have the determinant of this be positive. So any matrix that satisfies the orthogonality constraint is either rotation or a rotation plus a mirroring. And if there's a mirroring, then the determinant is going to be -1. But if it's just a pure rotation, it's going to have a positive determinant. So if you think about the 9 entries here, the orthogonality constraint imposes 6 individual constraints here. And if we think about taking 9 variables and eliminating 6 degrees of freedom because of the constraints, SO3 can be seen to have 3 degrees of freedom. This is a bit hand-wavy of an argument, but it should suffice for now. So there's actually only 3 degrees of freedom in which I can choose my rotations, even though there are 9 entries in this matrix. And so there's a lot of redundancy in this representation here. So one of the questions is, if we're trying to interpolate or if we're trying to represent rotations in a more compact way, can we do so with only 3 numbers? And the interesting thing is that we can't just represent them in terms of Cartesian coordinates. It's not equivalent. So the space of SO3 is not equivalent to R3. So we're going to look at 3 different representations of 3D rotations. And because we tend to represent these quantities as a bunch of numbers, a vector of numbers inside of a computer, they're each going to have some deficiencies when trying to represent the space of SO3. So as we've seen, 3x3 rotation matrices have too many numbers essentially, and we want to only consider a few degrees of freedom of that set of possibilities. So we're going to look at 3 new representations: Euler angles, axis angle representation, and Quaternions. So all of these representations are equivalent in the way that they can actually represent any rotation matrix. However, they have certain mathematical and computational advantages. So because SO3 is not equivalent, not homeomorphic to a Cartesian space of any dimension, we can't just treat these as numbers in a Cartesian space and blend between them in a naive way, for example. Also, for when we're going to be looking at machine learning, most machine learning algorithms deal with operations in Cartesian space, and we're going to have to deal custom with, if we're trying to learn things about 3D rotations, we have to deal with these in a custom way. So let's start with trying to build 3-dimensional rotations up from some basic intuition about 2D rotations. So if we're to look at a z-axis rotation only, so let's imagine this forward direction that I'm pointing at your screen here is the z-axis, and I have an x-axis and a y-axis here. So a rotation about the z-axis is just going to be a rotation much like a 2-dimensional rotation, although I keep the z fixed. So everything on the plane that you're seeing is going to rotate along with this rotation. And so I can imagine having this 2x2 rotation matrix in the x and y components of this 3x3 matrix. And then the z component, the 3rd row and the 3rd column, will basically be a no-op. It will basically keep all the z components identical. So we can do the same thing about rotations about each of the individual other axes. The y-axis and the x-axis all can have very similar types of representations with this general pattern of cosine, sine, sine, cosine, although in different rows and columns of this 3x3 matrix. So from these axis-aligned rotations, we can build a very natural kind of representation, which is that of the Euler angle representation. If we think about some arbitrary rotation, we can try to build them out of axis-aligned rotations. So these give you 3 different numbers, phi, theta, and psi, and they represent rotations about different axes. So if I were to, for example, rotate 45 degrees about the x-axis, 45 degrees about the y-axis, and then 45 degrees about the z-axis, I'll get this resulting rotation down there. And it turns out that we can represent any rotation matrix through some combination of Euler angles of this rotation about x, y, and z. So there's many different types of Euler angle representations, and we've chosen X, Y, and Z in the past slide, and that's actually a very popular representation called roll, pitch, yaw angles. However, there are all the other different types of conventions used in the literature, and basically if we think about the axes being chosen as variables A, B, and C, we can almost pick any combination of X, Y, and Z to put into this convention, and we have an Euler angle representation of the final rotation matrix as a parameter of these three, as a function of these three parameters, as Ra of phi, Rb of theta, and Rc of psi, where A, B, and C are one of the X, Y, and Z axes, and these are all axis-aligned rotations. So just to give you a sense of what the final results look like, if you're to take the roll, pitch, yaw convention, the final matrix that you get out is a bunch of cosines and sines multiplied together and also added and subtracted together. So you can get this representation in the bottom right here. And that suffices to represent all rotation matrices, and it's a very popular representation, especially in aerospace. So there are some disadvantages, though, to Euler angle representations. The first one is that if we wanted to get a basically complete coverage over the rotation space, we should choose the range of these angles cleverly so that we do achieve that sort of coverage. So, for example, the roll should be plus or minus 90 degrees, the pitch should be plus or minus 90 degrees, and then the angle can be, the yaw angle can be plus or minus 180. There's also singularities that happen, which are also known as gimbal lock. So if you had, for example, a ZYZ rotation, where you could, let's say that this is my Z-axis, here's my X-axis, and here's my Y-axis. So I could represent any rotation by a rotation of Z, rotation about Y, and then another rotation about Z. But if my rotation about Y is 0, then if I were to rotate about my first Z-axis, I don't rotate about Y, then my second Z-axis is actually aligned to my first Z-axis, then I have what's known as gimbal lock. There's actually a redundant representation here of any angle, of any rotation that doesn't have a pitch associated with it. The same thing goes for roll, pitch, yaw angles. If I were to pitch by 90 degrees, either plus or minus, essentially if I think about an aircraft pointing vertically upwards, then I can roll. The rolling is the same thing as yawing in that case. So this is known as gimbal lock because there's a mechanical structure called the gimbal that has been used in aerospace for a long time to figure out the attitude and pitch and yaw angles of an aircraft. And so basically you use a gyroscope with this kind of mechanical device. And when the angles of this device ended up lining up, then it would actually get locked in place, and the inertial effects of moving around didn't unlock it. And so this problem had to be dealt with other means. Another issue is interpolation. So Euler angles do interpolate in some relatively okay way. If you were to take two sets of Euler angles and just linearly interpolate between them, they do something. They go between the two orientations, but it's just that you have the problem of wrapping over, just like we had in 2 dimensions, and also the rotation that you choose, even if you do deal with a wrapping problem, still is not going to be the most efficient way from getting from one orientation to another. So let's look at some other approaches. So axis angle representation uses the curious and interesting fact that every rotation matrix can be obtained by rotating the identity matrix by some angle theta about some axis v. So if we were to take this resulting rotation here, which was the same as you get from a roll, pitch, yaw representation of 45 degrees, 45 degrees, 45 degrees, you could find that there's a rotation axis that actually rotates towards this result in fewer than 45 plus 45 plus 45 degrees. And so this axis here is actually the unique axis. So there's actually 2 unique axes, one going one way, the other one going the other way, where if you should look at the rotation matrix, it's actually an eigenvector of the matrix with the eigenvalue of 1. So basically this axis doesn't get modified by this rotation. So how does this actually work? Well, if we assume that there's some axis v, it's a unit axis, then there's an angle theta. Rodriguez's formula, created by Mr. Rodriguez, figures out how to rotate a point x about that axis by essentially thinking about how x can be decomposed about the component about the axis itself, and then an off-axis component. And I'm not going to go into the details about how to derive this, but in any case, you can represent this rotation formula in matrix form to derive the rotation matrix for any axis angle representation. So essentially, you can see here that there's this cosine theta times the identity term. You add on sine theta plus this cross product matrix term. So this cross product matrix does the same job. If you were to multiply this matrix by some vector x, then it would be doing the same job as doing v cross x. And then you have this final term with a 1 minus cosine theta coefficient times VV transpose, the outer product of V. So this is really nice. And the other cool thing about this is that you can also recover the angle and the axis from a matrix using these formulas here. Essentially, this is just basically an inversion of the formula that you saw on the previous slide. So this is very cool. We're going to be using this in the future to deal with interpolation. So with axis angle representation, this is a very popular type of representation because it's quite intuitive, but one of the issues is that it's non-unique. So if you're to rotate about a certain axis with a given angle, and if you're to rotate about the negative axis, about the negative angle about the negative axis, you'll get the same rotation. So one thing that you can try to do is you could try to constrain the range of your angle to some given range, like 0 to pi. And that kind of solves that uniqueness problem. But one of the other problems is that we now have 4 parameters representing the rotation. So we have the angle and then 3 axis parameters. The thing here is that we have to make sure that this axis is unit length. So we have this constraint that the norm of v is equal to 1. And this can be a bit problematic for a number of applications, such as in interpolation and optimization, sampling, or also machine learning. So one better way of representing axis angle rotations is known as the rotation vector representation. Essentially, all we do is multiply theta by v, right? So we encode the angle by the length of the vector. And this also gets rid of the problem that any zero rotation can be represented by any axis. So the zero rotation becomes a zero three-dimensional vector. This vector w encodes the angle theta with its length, and encodes the axis with the direction. All right. So this is also known as exponential map or rotation moment, but this type of representation cleans up a lot of the problems of axis angle rotations, and it's actually quite a nice encoding. Another representation that's very widely used is that of quaternions. So this is a really curious representation. Just the name quaternion just kind of says it all. It's like, wow, that's a really fancy type of thing, and so we're going to impress our friends by talking about quaternions. It's actually a very old generalization of complex numbers. So complex numbers were known to encode two-dimensional rotations with unit magnitude complex numbers. And for a long time, people were trying to figure out the three-dimensional analog of complex numbers. And Sir William Rowan Hamilton was busy trying to figure out this problem of representing three-dimensional complex numbers by trying to add a second complex number, j. So he wanted to have 3 numbers, z0, z1, and z2, which gave you some sort of three-valued complex number. But he's working so hard that his wife told him, you're really just killing yourself. Go take a walk. And out in Scotland, there's a bridge where he was taking his walk, and then as he was musing about his problem, a flash of inspiration hit him, and he realized that it had to have actually 4 numbers rather than 3. And with this, he found the inscription of on this bridge. He scribbled it down very furiously that these 3 complex number components, I, J, and K, satisfy these various properties. And so now this quaternion has 1 real component and 3 imaginary components. And it turned out that this was such a huge breakthrough that it became taught in all physics and math courses if you're to be a math major or physics major, and actually it predates the development of linear algebra. So actually people were like, well, what are these newfangled vectors and matrices? You learn quaternions first before we deal with this kind of funky stuff. So, but in any case, you know, ultimately we see that linear algebra won out in the end, but we still use quaternions for dealing with three-dimensional rotations. So what does this look like? So this representation is a unit quaternion that can map to a rotation matrix using the following formula. So Q0 here is the real component, and then you have these three imaginary components, and these are all constrained to have unit length 1. It's very related to the axis angle representation using this equation here. But in any case, you can see that there's no need to do cosines and sines in order to produce the rotation matrix from the quaternion. So there's some advantages there. So thinking about the space of 4 numbers that have unit length, we're actually thinking about a 4-dimensional sphere. This is actually the surface of a sphere, which is actually 3-dimensional, embedded into a 4-dimensional space. One of the weird things about quaternions, though, is that it's not just the 4-sphere that we're looking at, but a point on this 4-sphere and its negative actually map to the same rotation matrix. So this is why it's also called a double cover of SO3. It has some advantages. So quaternion multiplication is equivalent to rotation composition. There's some quaternion multiplication expressions that you can look, and it's slightly faster than matrix multiplication. There are also some nice curve interpolation formulas on the 4-sphere. This is called spherical linear interpolation, and this can give you actually geodesic rotations between 2 different points on this quaternion sphere with a bit of care. However, there are some disadvantages. One is that we'd have to deal with this unit length constraint, and there's also this double representation problem that we have to deal with during interpolation and other representation problems. So in summary, I'm not going to go through this, but this is a summary of all the different types of representations we've looked at. There's some advantages and some disadvantages of each of these. And if you're trying to pick a representation to use, then you'll want to pick one of these. There's no magic bullet that's going to be much better than anything else. I tend to prefer rotation vectors, although some people tend to prefer quaternions. But in any case, these are all valid representations of rotation matrices. Now, getting to interpolation, we can think about distances between rotations using the axis angle representation. So the angle of an axis angle representation is the distance from any rotation to the identity matrix. And so we can take that same intuition and try to find the distance between 2 different rotations. If we just take the inverse rotation of R1 times the rotation of R2, that gives us a relative rotation between these 2 matrices. And if I were to take the angle of that relative rotation, using this expression here, this is the minimum angle that we need to rotate from frame 1 to frame 2. So this makes a very good distance metric because, well, the distance from a point to itself, a rotation to itself is 0, and the maximum distance between any 2 rotations is going to be pi. Now, if we want to think about rotation interpolation between 2 matrices A and B, so we're trying to find some path x of u that goes from, if u is 0, it goes from A to u is equal to 1, which is B. So we can do this by thinking about relative rotations. So if we're to take the axis angle representation of A transpose B, then this is basically the axis angle representation of the relative transform from A to B. And if we're to recompose this into a new matrix where we scale the angle from 0 to 1, and then we pre-multiply by A, we're going to get a geodesic between the source and the result. So here's some animations of some randomly sampled orientations. So this rotation axis gets pulled out by this relative rotation here, and it's a minimal rotation between any source rotation to any resulting orientation. This is actually a geodesic in SO3. We're not going to go through and prove that, but you can just suffice to say that this is the best way of going between any 2 rotations in terms of minimum angle traversed. Okay. So to recap, we've looked at these different operations on transforms. We've looked at 4 so far. At some point in later lectures, we're going to be talking about velocities, but we've talked about application, composition, inversion, and now interpolation. So each of the 4 common representations of rotation matrices are going to be implemented in many different software packages. Clamped.math.so3 and also SciPy has a robust implementation of these as well. And we also talked about some of the notions of geodesics and distances in SO3. See you next time.